My name is Garrett Ransom. I work at Los Alamos National Laboratory, specifically in their HPC systems department. And I'm here to talk to you about MarFS Multi-Component. This is an open source file system that has been developed at the lab to meet our needs. So, you may have already heard about this before, but I want to at least give you some degree of background about the need for this. If you've seen Gary Grider's talk last Tuesday, some of this will already be familiar to you. So, the issue that we're having is that data sizes are growing significantly faster than our current long-term storage capability. For example, Trinity, our current supercomputer, has 2 petabytes of in-system memory and approximately 4 petabytes of flash. This is the burst buffer that you would have heard referred to in Gary's talk. Comparatively, our Crossroads system is going to be something along the lines of 4 petabytes of in-system memory, and I'm told 10 to as many as 100 petabytes of flash attached. That is compared to our archive, which is approximately 60 petabytes of total capacity, and that is constantly being filled, constantly near capacity. This is a tape system, and we're constantly having to buy new tapes to provide more data storage for these users who are just pouring into archive. Another issue with our current HPSS implementation is that the bandwidth of the archive is a bit limited. And it has an interesting issue in that it ingests data much faster than it is willing to return it. This can be a problem if you want to migrate off a system later on, because we've been writing into this HPS system for years, and if we ever want to recall that data to move it on to something new, it will literally be a matter of years to pull that data back. So we want something that has high capacity and can return the data to us in a reasonable amount of time. We don't want this to be a write and forget system. So what can do that sort of job? Well, we have parallel file systems such as Lustre, and those are great for high bandwidth, short residency sorts of data. We get some pretty crazy bandwidth out of those. They provide the scratch spaces for our supercomputers, but we tend to wipe those things about once a month, make sure that the data is not sitting there for too long because it's not particularly resilient. Now, you can provide greater resiliency to those systems, but it tends to be expensive to buy that much disk, to buy that much enterprise-grade disk in particular. And that sort of tends to hurt the purpose of what Lustre has been designed for. It's a scratch space, at least in our case. Comparatively, tape archive is very reliable. It's very slow, historically. Buying tape for bandwidth is incredibly expensive. Designing new tape systems can be incredibly complex. Streaming from all those tapes at once can be fast if you can do it, but buying that much tape, designing a system for that, is a headache. Also, both, at least historically, can suffer from metadata scalability issues. We want our users to be able to hammer these things. We sometimes see workloads where users will checkpoint their data and write out literally a file per variable that was in their run, which is a nightmare. So what's the solution for this? More tiers. That's always the storage solution, right? Just add more tiers. So this model is sort of a past, present, future look. Historically, we have in-system memory, parallel file systems to provide a workspace, and then archive, where if you actually need to keep anything long-term, you put it there. What we're moving towards now is more of a 5-tier model. We have in-system memory, the burst buffer, which is our IOPS bandwidth, sort of near scratch. The parallel file system, again, like a working space, you can probably keep it there for months. Then we have what I want to talk about, which is campaign. This is our capacity space. And this is where we're talking about residencies of years, potentially, and capacities of 60, 120 petabytes of data. And then archive, of course, will always have a place at the bottom. Now, is this too many tiers? Well, yeah, kind of. I mean, ideally, what you really want, as Gary discussed, is 2 major tiers. You want a high bandwidth, very fast tier for scratch space, that sort of thing, and then you want a high capacity, high resiliency tier. So what we're hoping is that over time, this burst buffer technology, this IOPS bandwidth tier, will expand, take some of the pressure off of in-system memory. At least, of course, you always need that, but we're hoping it won't need to grow as fast. And then this capacity tier, which will provide our resiliency, provide our long-term storage, and take some pressure off of archive so that we're not buying so much tape. So for implementing this, how do we actually implement such a thing? Well, object storage seems promising. It provides a flat namespace, a great deal of scalability, and erasure coding gives you the resiliency that we're looking for. And that allows us to buy cheaper disk, because at these sorts of scales, we don't really want to be buying enterprise-grade hard drives to store petabytes. But object storage has limitations associated with it. Machines love object IDs. People generally do not. And there are potentially billions of dollars in applications that expect at least some degree of POSIX namespace. Gary in his slides claimed it was trillions of dollars. Expecting these applications to be rewritten, some of which are very, very old, is not ideal. We want to at least have that namespace available rather than going pure object. So this brings us to MarFS. What is MarFS? It is a near-POSIX interface layered over distinct metadata and data implementations. So what I mean by that is we are actually literally storing our metadata into a parallel POSIX-style, POSIX-like file system, in this case GPFS, while we're storing our data as objects to our multi-component system. So the goal here is that you get familiar semantics. Users can interact with the metadata trees as they expect, but you also get the stability associated with those objects. And we can use cheaper disk as a result of that, at least for the object storage. And we can buy enterprise-grade SSDs, that sort of thing, to interact with the metadata for fast updates. But the objects themselves, the petabytes, can be stored to commodity hardware. So this is the way that that system actually looks. We have the MarFS library, and below that we have these two abstraction layers. We call them the DAL and MDAL. That's the data abstraction layer and metadata abstraction layer. And really they're just sort of an interface, something that you can swap out relatively easily. They provide an interface to the metadata and data respectively. If you wanted to store to something besides GPFS underneath, you wouldn't rewrite the MarFS library, you'd rewrite the MDAL. And then your metadata could go to a different system, something completely different potentially. Another aspect of this system that I wanted to bring up is that we don't allow users direct access to this in the traditional sense. I mentioned that they have this metadata tree, this POSIX tree that they can interact with. That is for metadata updates only. When you actually move data into this, you use a tool. In this case, you use Pftool. That's our parallel file transfer utility. This is something we've had around for a long time, sort of on a back burner. But recently it's been adapted, updated, so that it interfaces directly with the MarFS library. So you can point this at an enterprise file system like Lustre and point it at a MarFS path and say, stream this data in. Yes?
So if I have one of these trillions of dollars worth of apps that actually does F open and F write, will that just work? Or do I have to change my app?
Well, if you're doing that, you're probably pointing it directly at scratch space. And then you kick up this tool to do the move over, and it preserves that metadata so you don't lose it. So if you move it back, you still have all of that POSIX. I won't say always, no. But interfacing through this Pftool is just launching up a job. And you can, I'll get to that later on. But the fuse mount here provides a metadata view of the file system. So this is where users can go in and do chown, chmod, move, that sort of thing. And that can be directly acted upon. It's just moving data into and out of. You need to pass through this tool. As I mentioned, DAL and MDAL allow swapping of storage. But what I really want to focus on here is this bottom right corner called multi-component. This is something that I helped put together. So what is multi-component? It is cross-server erasure coding atop ZFS pools, at least in our case. So what this does is provide us failure tolerance at both the disk and the server level. So we can lose disks up to the point where we lose a pool, but even if we lose an entire pool, even if we lose an entire server or two servers, we can still read and write, we can still maintain availability of this data. It also, as I mentioned, allows us to use cheaper disk commodity hardware. We're not buying enterprise-grade hard drives for this. The erasure coding itself is performed through the Intelligent Storage Acceleration Library. I think that got mentioned at some point during an Intel talk. And this gives us the opportunity, as with most object stores, to get a lot of parallelism out of this. We can write to multiple servers simultaneously, read simultaneously, aggregate that data on our file transfer nodes. So here's an overall look at that to help you visualize it. So what we have are these FTAs. From there, we stripe out the data across these Z pools, perform erasure coding across the whole set, and you're writing individual pieces of those, either data or parity information, to individual servers. So that means if we have a power event, lightning is pretty common in Los Alamos. If we have a power event that takes out multiple servers at a time, there's still a good chance that even with whole racks down, we can maintain this availability, not just losing disks. Okay, so there's three main points I want to touch on with this. We're hoping for load balancing or scalability in this case. And of course, this is no different from a standard method of storing objects. We're looking for high availability, of course. As I already mentioned, we're capable of losing entire servers and a significant number of disks. And we're looking for a transparent architecture. Now, this is an issue we've had in the past, and I'll touch on that to a degree. Is why aren't you just using a standard object store? There are plenty of object stores. Why, oh why, would you write this? And the answer is that a lot of those object stores try to do things that don't necessarily apply to us. I'll touch on some of those later. A lot of them also tend to be black boxes. You write data in, you hope that it's secure, it tells you it's secure, and then you just eventually touch it again someday and hopefully get it back. And we've run into issues with this before. This was not our first cut at this. We actually did use third-party object stores to originally store this data, and we ran into issues with it theoretically having been secure, but it turned out that was not actually the case. So in terms of load balancing, the way that these objects are distributed is we write to pods, blocks, capacity units, and scatters. This is just a tree structure that we're distributing our objects across. So pod corresponds to a server set. We're doing a 10+2 erasure coding across servers. So in this case, it is 12 servers per pod. Block corresponds to a start point within that server. So it corresponds to a Z pool in this case. And that is where we begin the striping across these pools. Capacity unit corresponds to a level of Z pool, as in we have, in our production system, we have 4 pools per server, and you start at a particular level of those pools, so we're not writing everything to the same disk set. And finally, scatter directory is just a logical division. It doesn't correspond to actual physical separation, it's just a logical division, so we're not overloading directories. As I mentioned, we're looking for transparency here, so if an administrator goes down and LS's one of these bottom level directories looking for these object pieces, they won't get 100,000 entries, they'll get 100. So this is what that looks like in concept. The top level division that I added in here is a repo. MarFS allows writing to different repositories. So you could run a multi-component repository versus some other object store type of repository. And that's what this division means. In that, you get into the multi-component aspect of things. So as I mentioned, we have pods, these server sets. The individual servers themselves correspond to blocks. That is where you're starting your striping. And that's important because the objects tend to be overloaded towards the front of the stripe, as in they could end at any time after that. So we don't want to always start at the same server and overload it. Then the capacity unit corresponds to a particular pool within that server. And finally, their scatter directories, which again is just a logical division at the bottom level. So this provides multi-tier erasure. In our case, we're doing 10+2 across the servers, 17+3 across the disks within each pool. So we have to lose 4 disks from an individual pool in order to fail to read that pool, and we have to lose 3 whole pools in order to fail to read objects from that stripe. Now this was developed because we wanted to get higher reliability, particularly after an event where we had literally more than 100 drives fail at once. Turned out to be a software issue, but it caused huge fallout, and we were concerned that the standard erasure coding that we could use was not sufficient. So we went for this multi-tier structure, which we, at least at the time when we were looking at this 3 years ago, was not something that we had found elsewhere, at least not something that was applicable to us. So the multi-component library, libne, automatically responds to read failures, write failures as it goes. Now what this means is that as you're reading, you're only ever actually reading the data parts that you need. You generally don't touch the parity for a read. You just read the objects directly back from these Z pools in parallel. But if necessary, if you hit a read failure, if you get a CRC issue, you can engage that erasure code, read back the erasure parts, do the calculation on the FTA, and hand back data. And this is all opaque to the users, as in they get their data. Similarly, we do allow degraded writes. This is something that's configurable when we set it up. So you can say, I think that a single failure is acceptable for us not to lose availability. So for example, in the case of a 10+2, if a server drops, you can still write it as a 10+1 or a 9+2, and then you can later rebuild that stripe to full width. So any degraded objects during read or write are logged, and then there's a utility that crawls these logs over time to rebuild these things as we go, as we choose when we run it. It also has the ability to be run against an entire capacity unit. So if you did lose an entire pool, had to reformat the whole thing, replace it, you could rewrite all of the data back to that by running it in this sort of emergency mode. Now that mode can be run through MPI and threaded across all of our servers, so we can do it very, very quickly. But what you can also do is run it very, very, very slowly, as in maybe a few threads on a single server, and just have this chewing through data in the background to make sure that everything is as we expect it to be. We've had issues before with data that was stored and it was assumed that it was being checked, being verified, but it turned out that it's, with some object stores, they wouldn't actually correct that data, wouldn't notice that it was wrong until you did a read on it. And with some of this stuff that could be sitting there cold for years, potentially, that's not an option. So we have this tool to crawl it over time, slowly, not get in the way of user reads and writes, and verify that everything is intact. So now finally this transparency sort of aspect to it. This system is not designed to be overly complex, and in fact that's why we were able to implement something like this and get decent performance out of it, is there's a lot of complexity that we are ignoring because it doesn't apply to us. So in the case of MarFS, for example, we don't allow update in place of files. When you do a write of a file, you overwrite. You do the entire object start to finish, period. Now, for a lot of applications, that doesn't make sense. For scratch space, that doesn't make sense. But this isn't scratch space. This is long-term storage. This is a capacity tier. Similarly, with multi-component, really all this is this cross-server erasure coding. We let ZFS handle the bottom layer that's used in a lot of systems, so we trust it. And this organization here allows a lot of transparency. You can actually go into these ZFS pools, see the object parts that were stored there, ls them, cat them if you want to, but though that's a bad idea. And we also, when we write these things out, we pair them with manifest files, as we called it. It's a little info on what erasure coding was performed, the total size of the data, the total CRC for this data that is expected to be handed back. And this means that if admins are actually looking at these, they can get a sense of when it was written, what it was, what it's supposed to look like. Similarly, multi-component provides some utilities that go directly through libne so that you can read and write these objects directly. You don't need to go through the whole MarFS stack if there's a problem. You can just fire up one of these little command line utilities pointed at a path and say, give me a status of this path, what's going on with this object. You can similarly read or write directly into and out of it for debugging purposes, though, of course, that's not the way that we intend to use it. So this is what at a much lower level, this is what the actual objects are going to look like. So each of these blocks corresponds to a pool or a file that's stored to a pool on a server. And we stripe across these and then write out each part and then append to them for the next stripe. And we calculate erasure across each of those stripes. At the same time, we write out our own CRCs. This is something that realistically is not strictly necessary, and it's something that you can toggle off. Because we're writing to ZFS, we trust that it'll give us back good data, but just in the case of bad data coming out, errors over the line, or in the case of someday we may not be writing to ZFS, then we want to have these redundancy checks in place so that we can actually verify that these data blocks are good. So yes, calculate erasure across each stripe, write out each piece, and then attach these manifest files. Now I say manifest files. Originally we were doing this as XAdders, but these are being served out to clients via NFS, and we ran into issues with NFS not supporting XAdders. So we do it as separate files, and it turns out that the performance overhead from that has been surprisingly negligible, though we can go back to XAdders at any time. So to better understand this, I want to give you a sense of the way that we actually deploy this system. So we have interactive FTAs, batch FTAs, object storage servers, and metadata servers. So the interactive FTAs are user accessible. This is where users log in. This is where you mount your other file systems such as Lustre. And this is where we provide the MarFS campaign fuse mount. And this is just an NFS export from one of the batch FTAs that provides a metadata view of the file system. So users can see the tree of their files. They can LS it. They can do metadata operations. But if they actually want to do data movement, they should fire up Pftool, and that's launched across the batch FTAs, of which there are significantly more. So the batch FTAs have a MarFS fuse that's mounted both data and metadata, and they export metadata only to the interactive FTAs, as I mentioned. And this is also where Pftool runs. This is where it actually interacts with the MarFS library. This is where you actually have multi-component functioning and writing out to these NFS mounts, writing out to these servers. Then there's the object storage servers, of course, and then the metadata servers for interacting with metadata from both the interactive FTAs and batch FTAs. So here's a rather busy diagram of the whole thing. I put in some complexity here that I haven't talked about. Maybe I'll talk about it if people are interested. But the general thing I want you to see there is that the library interacts with the DAL, which interacts with multi-component, uses ISAL to perform erasure coding across the servers. Then we have this rebuilder utility, along with the utilities that can be used for reading and writing and getting status on objects that interact directly with that multi-component library. And then on the other side, just if you're interested, we have a quota tool for managing quotas through the metadata, and the garbage collector, which interacts with a whole ton of parts of the system. It's a bit complicated. And the reason why we have a garbage collector for this system is because we've literally had users who go in and say, oh, that 4 petabyte tree, I don't really need that anymore. I'll just do an RM-RF on the whole thing. And suddenly the system is just sitting there doing deletes for all of these operations while we've got users trying to put good data into it. So instead of doing that, we mark it as trash, garbage collected later on, out of band, maybe overnight. So as I mentioned, this is already in production. Our current production system has 5 interactive and 25 batch FTAs, grand total of 30. So the 25, again, are what Pftool runs across. We have 60 petabytes of total available storage, and we're getting, I'm told, roughly 25 gigabytes a second in aggregate bandwidth. So that's 25 gigabyte a second read, 25 gigabyte a second write. And it's slightly faster for read. Again, that's at least somewhat by design, because we wanted to be able to actually get data off of this. We don't want people writing into it for years and years, and then when we go to read it back, it takes a lifetime. And at present, NFS seems to be the bottleneck in this system. It's probably a little weird that we're serving out so much data over NFS all the time. So that brings us to our future work. We are currently in process of getting a InfiniBand RDMA implementation of this into production. So instead of going over these NFS clients, NFS servers, it would just be a direct RDMA connection to paths on the servers, which we expect to greatly improve our performance. We're also looking into better administrator controls for diagnosing issues, helping users, that sort of thing. Capacity unit migration is an interesting topic, and that's something that the code for has been completed. It's still being looked at, reviewed. But the concept there, if you'll let me go way, way back on you. Yeah, maybe this will work. The concept there is that if you want to do a scale out of this system, at present it's a bit of a pain because you probably have to add an entire new pod of servers. And then you have to read all the data out, write it back so that it's properly striped across these servers, properly distributed, so you're not overloading your original servers. That's not great. So what this capacity unit migration is, well, how about we just enable you to add some disks to each of these servers, create a new Z pool, a new capacity unit layer, and then we'll just do a move local to the servers. So we're not sending any data over the network, we're just moving it between Z pools on the same servers. This also, at the same time, includes code to allow for hashing to be adjusted based on the capacity of the disks that you're writing to. So for example, if those new disks that you got in for expanding capacity are significantly more dense than your previous set, you can adjust your hashing so that they get hit harder. Also, we've been told that we have an issue with documentation. That is definitely true. Our internal documentation has been significantly updated. And we're hoping to make that more complete and then very soon more available publicly. Finally, one thing that we're looking into is whether a MarFS system that is backed by tape could act as a next generation archive. So this would look something like that. The concept is that you have a batch interface to this, and then that batch interface interacts with Pftool. Pftool would run scanning metadata, scanning trees, telling you how much data it's looking at moving, telling you how long it expects it to take, and if it's even possible. And then out of band, overnight, something like that, jobs would kick off to actually move that. And that data would hit the MarFS Multi-Component landing zone. And then from there, we'd actually take the ZFS files that I mentioned are on the far back end and put them into a tape system. In this case, Tivoli. Similarly, recall would work just the same way. We give Tivoli a list of objects, say, hey, we stored these things to you. They're just pieces of objects, but it doesn't matter to Tivoli. Pull them back, put them onto those servers in that disk landing zone, and then you could just do a read through multi-component like everything else. So again, this is all open source. You can find MarFS on GitHub. Multi-component is on GitHub, Pftool, so on. And we're definitely looking for input on this, collaborators on this, people who are interested. You're free to take the code and use it for whatever suits your fancy. But we'd definitely like to hear what you have to say. And with that, are there any questions, anything else you'd like to hear about? I can talk about other aspects of MarFS if you want, or just multi-component.
One of the benefits of tape is that when you have a cartridge sitting in a library, it consumes zero power, basically. So there are some scaling limits, but for your practical implementation that you're doing where you just don't have enough power?
Well, I can't speak to how much of a consideration that was in designing the system. I can tell you that we have a ton of power and need a ton of power. And the actual power consumed by these disks compared to Trinity, which consumes, I can't remember the number, 10 megawatts, something like that, is relatively insignificant. That doesn't mean it's not a consideration. Tape definitely consumes less power, but in this case we thought that actually getting that data back would be more valuable, and we didn't want to design a tape system with all of that complexity and all of that expense for suiting our needs. I hope that makes sense.
Yeah. I had about 50 or 60 comments, but I'll maybe just make one or two.
Okay.
Is It's almost identical to the system IBM developed from NASA 5 years ago and has been marketing commercially for the last 3 years. But what kind of took the gas out of that was the policy-driven user tiering available in products like GPFS, where you can essentially create that at the file system layer based on user policy-driven. That's just one comment, but it looks very much like the system down in Houston.
Okay.
You might be interested in talking to those guys. If you're interested, just let me know. Another couple of comments. The bandwidth that's driven most of the backup applications that wind up as archive data are sustained sequential writes. In fact, almost all of it. And the problem we've been having is that the tape systems always overrun the capacity of the disk systems bandwidth-wise. We can never get the bandwidth through the disk systems that the tape systems will take. And the reason for that is that most of the tape backup applications are multi-threaded, and they're driving into 32 drives in a library, for example.
Yeah. So there's a lot to compete with there in terms of tape, in terms of actual throughput that you can get by streaming to tons of tape at once. But my impression is that the difficulty associated with that is, of course, there's latency, that sort of thing, but that's not necessarily an issue. It's the expense of buying the tape. It's the difficulty of maintaining a tape system that can return that data to you effectively. And then also we are getting a great deal of parallelism out of this because we are writing to pools of 20 disks across 12 servers simultaneously. Now, I'm not saying that you're going to see leaps and bounds above a tape system that's designed explicitly for bandwidth, but we're getting a great deal of resiliency out of this. We're using commodity hardware, so it's cheaper, and the performance is actually, I think, pretty significant.
Another comment would be, products like LTFS, you're familiar with LTFS, which allows you to mount.
Yeah.
Yeah, it allows you to mount onto a workstation in what looks like a E or F disk or a drive, and allows the user to see a directory file structure like it's on disk, but he's really dealing with, logical structures that are stored on tape.
Yeah. So
do you have any plans in that direction, or for allowing users in a workstation to get access to the deep storage data?
One thing that was sort of exciting about this was the concept of NFS exporting these metadata mounts, and part of the reason for that was the thinking was you could put that NFS mount anywhere. It did not really matter where you threw this thing, and that's metadata only. In terms of data movement, you need to go through this tool, and that is a limitation, but our current HPSS system actually has the same limitation. You have to go through that through, I think it's HSI, PSI are the tools that we use. And that's just because the performance that we're looking to get out of it generally requires some sort of advanced tool set to interact with it. I hope that makes sense. But this metadata tree provides users a view into it. We're looking into a concept of indexing these things. This was something that Gary mentioned. And he's got a cool tool that I don't think he's ready to present on yet that would pull this metadata information, present it to users in an interesting way. Yes. Yes.
If you can provide a client piece that actually goes on a user workstation, because one of the characteristics of the 80% of the data that really winds up for regulatory or legal reasons, 80% of the data in the world today belongs on tape media. It doesn't belong on spinning drives or on flash for that matter. But the use pattern, is below the object storage, middle access profile that object storage has. It's a use pattern where it sits dormant maybe for 4 years until there's a lawsuit, and then somebody needs to pull it up on a workstation.
Yeah. Yeah.
So that would be a nice enhancement for you. I just suggest that.
There are definitely applications for archive, and that's sort of why I brought this up. We do want to have tape available at some level, and the hope is with this batch interface it can be presented with a web interface, that sort of thing. So an easier way for the users to interact with the archive than it has been in the past. Also because we're not giving direct access to them through scripts and that sort of thing. we're hoping to take some of the load off and have people store things that they really, really need. Because I've heard some horror stories from people talking to users, as in like, oh yeah, I've been writing data into HPSS since 1980. Have you ever read any of it? No. But you never know when you'll need it. So this capacity tier is designed to be someplace where users can throw those large quantities of info. If they need it, they can get it back.
On-premises place, it's more for on-prem than it is for off-prem.
Yes.
But if you had a replication component which allowed the backend to take immediate portability, you could dig into that Iron Mountain market space.
Yes, in the case of LANL, so I understand from a business perspective that is a huge asset. In the case of LANL, that's not something we've explored because on-premises is what we do. As in, we're not going to be moving this data off-site.
If you had an asynchronous packetized ability to move the data above just the index data, but the data in the servers and the data in your MarFS system, so that a remote entity, another MarFS system, could receive media that was either replicated or
yes,
you would be addressing the out of risk region market, which is
yes for offline.
Right?
Yeah,
that's a big market space. And
yeah,
it would have a really nice play, in that market space.
That's definitely true. So yes, again, this is always being expanded, and it is open source. So feel free to take a look at it, tell us what's wrong with it. But yeah, we are still developing this currently.
Okay, I'll shut up.
No, I appreciate it. Are there any other questions, comments, concerns?
Just an observation.
Yes.
At least the last one I talked, there are people who are commercializing some of the campaign storage, and so we'll probably have to talk about that next year. We're certainly open to them coming and talking, and they'll be out and about, publicize their stuff. But this is a development conference. We really don't focus a lot on much of the markets, go-to-market business.
Anything else?
Quick question. Why did you consider laying this on top of Swift or OpenStack? Other things that's already out there that provide some of the basic functionality that you already.
As in other object stores, yes, absolutely. Now, unfortunately, I came into this project after they had done a lot of this initial investigation, but I can tell you that they looked at a number of them and for one reason or another felt they didn't suit their needs. We were actually using a third-party object store for a while to handle this, but our setup is not standard in any way. We use diskless nodes, that sort of things, and we think that this might have caused the software to behave in an unexpected way. We ended up with objects that, by all rights, should have been provided back to us by this system that failed to be returned. And it was a black box to us. We didn't know what was going on inside. We didn't know why it failed to return these things when we had plenty of disks online that it should have been able to do so. So this has kind of led out of that. The other aspect of it is many of those systems try to fit a more general purpose application. As I mentioned with MarFS, we don't do update in place, for example. We don't do file locking. Every write is an overwrite. The most recent overwrite wins. That's a huge loss of complexity in terms of the system and a degree of overhead as well. So what that means is that implementing something like this has actually not been all that difficult, and we can write it specifically to our needs. Welcome. Anything else? Okay, thank you very much.